Nesta primeira sesión da mañá voulle pedir ás 4 persoas expertas que nos van a acompañar que se vayan achegando ata o escenario. Eles son Pekka Ritvanen, tamén vai estar con nos Oliver Kläusler, Michael Kern, que poden ir achegándose ata este escenario, e tamén nos acompaña Ewellyn Capanema. Con eles o que imos facer é coñecer esas innovacións que se están realizando. En definitiva, queremos buscar respostas para novos produtos e tamén para solucións a través das frondosas. En primeiro lugar, imos comezar con Pekka Ritvanen, que venden de Finlandia. El ten unha longa experiencia nas industrias do metal e da madeira e, ademais, desenvolve o seu traballo profesional nunha empresa que é precursora na industria da tecnoloxía dos procesos de modificación en termomecánica da madeira. Así que imos escoitar xa a Pekka.
Thank you. Good morning, ladies, gentlemen, attendees of the seminar. I have, my topic was experience from the use of birch in different applications. So first to be, microphone. This one. This one. Is it open? Okay, good. I was about to walk around the stage. Sorry to make you a disappointment, but I'm speaking fully out of the context, but I will come back to this later. First of all, yesterday there were exciting presentations concerning different approaches of the common problem that we are now facing, and I picked many issues there, and I try to cover them through my presentation. But first of all, Avantwood is a company that was established 2016, and we are specialized in thermomechanical timber modification, as we say, TM, and when we put the trademark there on top of, so we have 3 TMs in the name. Let me see what happens. Here. I'll go this through very quickly. Maybe I even skip this. So this is the main frame, because that is too much technology. I'll come back to that. So there is the global problem as we see it. A lot of CO2 emissions in nowadays building construction industry. We have a lot of wood waste. We want to improve the utilization rate of timber. And there are, as we heard yesterday, there are hundreds of underutilized, low-value wood species that could be utilized. Our solution is here an integrated technological unit that combines the drying of timber, densification of timber, in order to enhance the mechanical properties, hardness properties, dimensional stability, equilibrium, moisture content, permeability of the timber, so forth and so forth. And there are few boxes. This is integrated, and then we have the key issue is our patented control system that we apply in the process control. And that's about it. No chemicals and sustainable. I want to highlight a little bit the philosophy that we are we are approaching this problem. And there has been a lot of keywords in this seminar, but maybe first time I say artificial intelligence, which is on a high level future technology that will solve all the problems from climate change to social equality, whatever. I hear politicians using that word a lot. But here is our approach to the problem, because artificial intelligence itself doesn't say anything. It's two words. I'll put this first. So, from our prospect, the artificial intelligence is, first of all, deep sensing. One step back. We have a lot of, can you hear me? A lot of different input parameters in the timber, and then at the other end, there are a lot of customer expectations coming up, like color, hardness, strength, density, dimensional stability, and with the existing solution, when you try to timber, you get out standardized 2x4s, moisture content being about 18 to 10 or 8, and that's about it. But we are solving, and this is never-ending story. So we are, first of all, using the neural network mathematics to find the correlations and causalities between the inputs. Is there a laser here? Yeah. It doesn't. It works here. It works here, but not here. Sorry. So we aim to find the correlations and causalities between the inputs and the customer-specified outputs. Hopefully I go to the right direction. So that is deep sensing for us. Then we apply machine learning, so genetic algorithms, to continuously improve the process parameters in order to get improved end product and customized end product. And then as a whole, there is artificial intelligence that has the ability to learn like human. And I see artificial intelligence this way, that you need to have the application, not talking only about the general level. Okay. So this is a brief presentation of our process, very general form. So you have green timber that you put in, and simultaneously we apply a certain mechanical density towards the timber. We don't use sticks, we use aluminium cell plates. Three reasons for that. And we can apply a mechanical pressure on timber in the beginning, just to hold them straight, avoid warping, twisting, things like that. And then we increase the temperature. We take care of the relative humidity and all the things. We can, so to say, listen the timber, because when the parameters are wrong, the first thing that the wood starts to make is emitting so-called ultrasound, around 150 megahertz emission to the microcracking of timber. So then we know that the parameters, process parameters, are getting wrong, and they have to be adjusted. We can also measure with the electrical impedance spectroscopy, the moisture gradient of the timber, so that we know online information about the wood to be modified, so where it's going, and we know exactly the moisture content of timber, so we know, do we have to slow down or even go faster? That is the continuous learning when we are applying the genetic algorithms and mathematics. And then timber dries to the either to final moisture content, or if the customer wants, we can continue the process immediately without any loading, unloading processes to thermal modification, thermal treatment, as they say. And then we can modify the timber according to customer requirements. And the process itself is quite fast. I have some examples there, which means that we can reduce the process lead time by, say, 90%. If that is too much, then I say 80. And that leads us to the ability to customize the products, and the semi-finished goods and the inventory is not that big. So flexibility. Let's go where I'm going. This is one example of the unit in Slovakia. And yeah, you can all read. There is all that I have already said, but I added some here slides. That's why. What are the advantages of the product? As said, customized products, increased density, high dimensional stability, because we lower the equilibrium moisture content and also improve the permeability of the wood. Sustainable, no chemicals used in the process. You may select the application that you want to do. It's not the I have nothing against UPM or Stora Enso or Metsä, which are the big Finnish companies, but obviously you cannot order anything specified for you. The processes are mass production paradigm based, whereas we want to have it as you would call mass customized paradigm in the process. I'll take a little bit back. Yeah, so this is overall, Andreas, you discussed yesterday about the value chain and creation the new value chain. This is how we see that in the forest you have big logs, you have small blocks, and then you have the all the minor parts of and when the investment point of view, if you use the big logs and you would like to have a huge sawmill to utilize them, it's hundreds of millions of euros, like Metsä Group in Finland, they are doing, I guess it was 300 million euros, the complete setup of the big log sawmill. But what we are saying, take the small logs, because there are quite a lot of it. You will tell more about that in the forest. Then you saw it. I'll come back to this later. And then, as you see, there are side stream dropping down, and then you get the pulp and energy wood and screening, drying, pelleting, and you can utilize also the side streams in the energy purposes for all of these. Nothing extraordinary, but in our opinion, this leads to improved utilization of all the wood particles in the forest. Now I'm trying to. This is our testing unit. So what we call, as you remember, talking about the artificial intelligence, one keyword is there is the digital twin, where you can test the process parameters. We have a physical twin. We can make with this, it's about 1.5 meters long. We can make the modification schedules of different species, and when they are being approved, then we can kind of upscale the results to the customer, and then we can provide them with the new modification schedules. And when I said that we cut off the lead time by 90%, it means that the customer can make a new product creation much faster than with the conventional way. Yeah, that is already spoke about that. Also spoke about the benefits. Megatrends, we discussed about those. We believe that there are, in our business model, that there are 4 megatrends: sustainability, renaissance of the wood material, resource scarcity that we have been discussing, and then the digitalization and artificial intelligence, which is our core competence. And those megatrends will affect all the society, customers, technological development, competencies, and so forth and so forth. So that is the base. But now I'm coming to business case example. One is, I'll go this through fast, a multi-layer parquet. Usually when you make, for example, of oak, multi-layer parquet, you take a plank of, say, 50 millimeters, and what do? You try it around 3 months, and then you saw it, the dried timber, with the multi-plate saw frame, saw verticals, whatever. Good morning. But what we propose, instead of that, saw the green timber into lamellas, and then check what is applicable in parquet industry, and then modify only the about 5 millimeter planks. And we have done that with oak, and it takes less than 1 day to dry them, and then you can apply them on the parquet. So 3 months lead time, again, maybe 1 week. I have been in the situation where the customer would like to have a white oak parquet, but the parquet factory said, sorry, we have only normal or regular oak, and that they are now drying, and it will take another 2 months. And both were disappointed. The customer didn't get what he wanted, and also the parquet factory, they have to give a 50% discount for obsolete, from their eyes, obsolete material. There is the same but I'll skip it. Then, since we are active globally, then we had a case in Vietnam and Malaysia. We have improve the utilization of acacia rubber wood. And here you can see the results. We reduced the lead time by some 85–90% and simultaneously improved the mechanical properties.
Sorry, Pekka, we are out of time.
I am out of time, that's why I'm...
2 minutes, please. Thank you.
And we discussed, that's very typical for me, we discussed about this building in Helsinki, Löyly. We brought there 18 kilometers of glulam board, and if you take a close look, no, it doesn't work. It's all made of small diameter timber. And the blocks of the building, they were 75 millimeter thick, 18 kilometers of wood, 6,000 different pieces, modules. So far since 2017, zero complaint about the material. Right, and now I'm running through. These are from the inside. These are made of cores, as you see, residues from the plywood industry, which has no value, and we converted it to a valuable end product. The value of the cores is something like 30 euros, and then we sold the material around 800,000 euros per cubic meter. Here is from the forest, and here is also. There you can see that. You can see the glulam board. We have applied only small diameter timber. I would like to discuss with you about the logwood, our innovation, but not this time. Yeah, everything is made of that. There is juvenile teak plantation and falcata. They are all over the world. This is one I have to have a minute for this. OPT, all palm trunks. Source of a global catastrophe in terms of CO2 emission. There are 100 million cubic meters of OPT that you can utilize, and 100 million cubic meters per annum every year. What we have made, we have converted it with our process in the usable board from zero-cost material. And this this is the final. We are now in a process to put on. Sorry, yellow card. In Bhutan, and not going through the wood species, but the Bhutanese, they brought us 31 species of wood, and we used 33.5 hours to modify them and give them the feasibility study. And now we are in the creation of mindfulness city in Bhutan, where they are building up a wooden city bigger than Singapore. That's it. Okay, thank you.
Pois continuamos de Finlandia, ímonos ata Suíza. Neste punto imos escoitar a Oliver Kläusler, que a súa etapa profesional está centrada en temas relacionados coa I+D na industria da chapa e da madeira, tanto en Europa como nos Estados Unidos. E, por certo, que un dos seus últimos produtos é a primeira tarxeta de pago en madeira, sen ningún tipo de plástico.
So thank you very much for the introduction and also for the for the invitation. It's a great pleasure to join this symposium. My name is Oliver Kläusler, and I would like to introduce you briefly into our Swiss Wood Solutions AG. I have to change the slide somehow. Okay, yeah. Was it this one?
Yeah, no. This computer is only for seeing the presentation. You have to pass here and
okay.
On the arrow.
All right, so I don't touch the laptop. Okay, thank you. So I would like to introduce you to our. I didn't touch it. Yeah.
Down arrow.
Ah, that's the other one. Okay, thanks. Swiss Wood Solutions AG. And then I would like to give you a briefly insight into our technology, give you 3 product examples, and then I would like to finish with a brief call for action. Actually, our Swiss Wood Solutions AG is a technology incubator and business incubator. We are a spin-off of ETH Zurich and EMPA in Switzerland. Now we are in the 8th business year. And our basic idea is to be an incubator, means that we create ideas about new wood application fields and wood application technologies and products. Sometimes we do it by ourselves, sometimes we have impact or input from outside, talking to customers, to partners, to society and so on. Then the second step is that this idea goes through our checklist. So we do the business check by first market analysis, and we start to create a business plan. Then we check the legal, the IPRs, certification requirements and regulations, which might affect this new product or the new technology. Then we go to the next step, which is a check of technical feasibility. This is then the third part, not the first and not the second. Technology comes as the third. And then we go through our lab prototyping, which we can do in Altdorf, in our facility, and also the pilot production. This is also done in Altdorf. So that's then the third picture. And then next step would be to go for the showcasing, which means that we do our product pilots and we show it to potential customers, to players in the specific industries and so on. And they give us their feedbacks by saying this is the right product for us or the wrong product. You have to change it like this, like this, like this. So we more and more get closer to the final product definition, and then we can go into the final market exploration with this specific product, and also finalize the analysis of costs and pricing. And at that step, then we talk to our customers and to our partners, because we don't want to go for the big upscaling. So it's not our idea to invest millions of euros into a production facility. Our idea is to license the technology out. So we give licenses out, or we also can go into a joint venture, or we can also go into a technology buyout. So we have different options here. So our customer and partner is then by himself stepping into the serial production. Also marketing and sales are under his label. So he's the one who's going outside with his label. So the product is then his product and the technology is his technology. We keep the IPRs on our side and license this out to him. So in the end, the customer can outsource his innovation risk to us. And he increases his chance of innovation success. That's the basic idea of our technology and business incubator. And this time it works. So let me give you a brief intro into our technological approaches. We have more than one, but the core technology is the green TM process. It's kind of related to what Pekka told us. It's not really the same, but it's coming close to it, a little bit different. And we also apply it to different materials. So it's always a combination of timber or veneers plus additional other materials. This is not necessary, but sometimes it's needed. So with this process, we can modify also hardness, density, color, mechanics, dimension stability, and we integrate additional functionalities. This can be optical functionalities or electronic functionalities So we add something to the wood composite. This is an example, just to give you an idea about the machinery which is needed to do this process. Of course, you need a special machinery, as you can see. For example, when we go for the beech example, and you would like to densify it, let's say from 740 kilograms per ton per cubic meter up to 1 ton per cubic meter, then you would need to have a machinery that is at least capable of pressing with 8 megapascal. So you cannot do it with a standard wood industry machinery. You need really something special. It's just one example. In the end, the material remains highly anisotropic, as you can see. I mean, the resulting mechanical behavior is, among other parameters, strongly influenced by the angle between the grain and the densification direction, but also depending on the load direction when you use the product in the end. So you really need to know what you are doing with the wood and what the product is in the end needed for. Otherwise, you cannot really optimize the process. So as you can see, when you, for instance, go for a densification in radial direction, and then you test it by a compression test, let's say in longitudinal direction, you have a strong correlation between density and compressive strength. That's the diagram on the left. But when you do the same densification process and do then the compression radial, then you have this correlation not at all. So you need to know in the end what you do with the product, and you need to adapt the process to this. But in the end, our material is not brittle, it's still remaining its highly appreciated ductility. This works. Okay, now the examples of our products. Just 3 of them. One is Sonowood. Sonowood, here on the left-hand side, you can see a Stradivari from the Henschel collection. And Christoph Henschel came up with the idea to improve the sound of his Stradivari, which was quite a challenge. And we said, okay, that's quite ambitious. So he took away the ebony fingerboard and the string holder, so the tailpiece on the left-hand side, and we replaced the ebony by spruce. So this is specially modified for this application, and we have a very high speed of sound conductivity along the grain, and we have a very low acoustic damping. This depends on the wood species and on the modification process, and in the end it was really what he thought is needed for his instrument. And in the end he's still having and playing it. It's now 3 years ago, and he's still happy with it and says, yes, Stradivari would have had applause to this. So, yeah, and then the second picture is, there you can see the black one is a beech. So standard European beech, just going through the modification process. So it's black like ebony, and the blackness goes through the whole crosscut of the timber, and it's still green. So you can take the tailpiece and throw it back into the forest, and the fungal decay will just rot it away. So there's no artificial color in this black beech. You can see also on the right-hand side the clarinet. We are starting to go also in woodwind instruments, and as you can see, the Pacific Quartet Vienna is one of the quartets playing with our material now for at least 3 years, and they love it because it's it improves the individuality of their instruments, which artists sometimes like and sometimes hate. So it's really an individual thing. But they can travel all over the world without any CITES restrictions, so they have no trouble with customs, with traveling or with the trade of the instruments. So they have also no reputational risk. So when you are on stage playing, and after the concert, some people come and say, you know what you are playing and where this wood comes from, because this is tropical something, then you are completely on the good side, because they more and more step into the stage where their high quality instruments are free of tropical woods. The next example is our wood pad. These are shin guards for football players. There are more body protection products coming up. This is just one example. and they love it. It's CE certified safety from FSC certified wood. So we also passed these impact resistance tests which you need for professionals in the sports sector. And this is a veneer-based product. So for the top you need a high quality of the veneers for the aesthetic reasons, but for the next layers which are invisible you could take also other kinds of veneer. So there's not so high quality needed. But people love it. It's an alternative to plastic shin guards, and it's lighter and thinner than the plastic shin guards. Currently you can buy them, for instance, on the web shop of FC Zürich. It's one example, also FC Luzern and others. And our ambassadors, here you can see Ana Markovic from Croatian national football team and Renato Steffen from the Swiss national football team. They will not switch back to plastic anymore. And our licensee here is the Woodpads AG from Switzerland, but it's possible to spread this technology, this basic idea also in other application fields or to other licensees. And then the third example, I think I'm still in time. Third example, our wood cards, our timber cards. This is the world's first plastic-free wooden payment card, and it's a high-precision product, as you know from standard payment cards. And on the upper right side, you can see that this product is made from 5 layers, and including the electronics, it in the end sums up to 0.83 millimeter thickness, so like a standard timber card. And yeah, it's still compostable. Yeah, you can, despite the max drive and the electronics, you can compost it at home in the flower pot if you want. And so it's really getting away from PVC plastic. Yeah? So I think this is a nice example that wood can be a good ambassador for a quality of wood as such, because wood can make it. We can enter highly precision application fields if we do it in a good way. And this is a kind of ambassador nearly everyone has in his pocket, and it's worldwide. So last year we produced and sold 100,000 of these cards, and the GLS Bank gave this into the market to their customers, and they had 95% positive feedback. So this year they will change their whole contingent of cards completely to wood cards. So this year, together with our licensee Copecto, which is on the left side, Copecto in Germany, we are right now installing the big serial production in Germany in their standard plastic card production. So it's now a bypass where the wood cards come in after the 4th production step, and then for the next 10 steps the wood cards go in line with the PVC cards. And they also want to turn down the PVC part year by year and go up with the wood card ratio. So we are wondering how this will turn out. We plan 1 million card for this year and then 3 million for next year. And but that's the business plan. So we will see. Hey, you need to have goals. That's clear. Yeah, and we can apply it to different wood species. So in the middle you can see the maple version. Also the lower picture on the right is maple, and then the SRF picture in the middle is spruce, oak and cherry. So we can also apply it to different wood species. So yeah, that's my last slide. Let's keep innovating. Feel free to contact us for your next innovation. You see we have happy customers on the right hand side. This was the photo was taken on the day when we signed the license contract with Copecto, and they are still happy. I mean, it's 1 year ago, but they are still happy. So let's do the jump together from our incubator to your business, and thank you very much for your attention.
Continuamos percorrendo países europeos para coñecer máis innovacións en materia de produto, neste caso, Ímonos ata Letonia e facémolo da man de Michael Kern, que gran parte do seu traballo está precisamente no asesoramento aos arquitectos, pois para poder analizar desas posibilidades que ofrecen os produtos, especialmente na construción con bidueiro. Así que, Michael, cando queiras.
So, good morning also from my side to you, and thank you for the invitation. Yes, today I will try to show you our way to sustainability and the using of birch as a raw material. But first of all, I would like to take this opportunity to briefly introduce Latvias Veneris for those who don't know Latvias Veneris, because we are the world's leading manufacturer of birch plywood solutions. And the history of Latvias Veneris dates back to 1873, when the first mill, Latvias Bērs, which means Latvian birch, was founded. And after the declaration of independence of Latvia in 1991, a close joint stock company, Latvias Veneris, was founded in 1992 by a group of numerous employees of the mill. So, and our production is focused on the Baltic region and includes a total of 10 mills in Estonia, Lithuania, Finland, and Latvia. Latvias Veneris employs approximately 2,500 people in 14 countries with an annual turnover of approximately 345 million euros. So, and for the sales of plywood, what is our main segment? You can call it also our DNA. We have 12 sales offices worldwide, most of them in Europe, but also in North America and in Japan. We export our plywood to almost 70 countries around the world, and all materials what we use for our production are legally sourced and comply with the wood safety regulations of the European Union. So, and also our main focus is on the production of birch plywood. We are also expert in other areas. And for example, we grow birch seedlings in our own tree nursery, which we then offer to forest owners and forestry companies. We are also active in forestry and offer certain services such as reforestation, soil plantations, preparations, planting and maintenance of forest areas, timber transportation and other forestry work. So, and we have also our own metal factory, working factory, where we manufacture and assembling all necessary equipment for our own production and research, but also manufacture machines for other customers. And like any manufacturing company, plywood production has many different byproducts, and this gives us the opportunity to develop other products with higher added value. And we have therefore identified ways to use 100% of the byproducts we produce, and one of our latest innovations of the use of byproducts is the extraction of betulene from birch bark. And even as a plywood manufacturer, we have also our chemistry department, where we are working on sustainable binders, and but more on that later. So now a few words about the forest structure in the Baltic states. We currently have 45% of land cover, forest land covers in the Baltic states. So with Latvian and Estonian, we have around 52 to 53%, and this is well above the EU average of 40%. Only countries such as Slovenia, Sweden, and Finland have higher percentages in the EU. And approximately the half of the forest is owned by the state. So in this graph on the left, it shows the steady forest growth in Latvia since 1935. The main species are pine and spruce, dominating in the softwood sector with 52%, and followed by the birch with 30%, and this is the strongest species in the broadleaf sector. So, and I think this slide gives a good overview about the fact that birch is a pioneer of the forest due to its high natural level of regeneration. The comparison with species such as spruce and pine shows that a higher investment in planting must be made here. And in order to internalize the resource potential of the birch species in the northern Baltic Sea region, we can speak of more than 1 billion cubic meters of birch trees. This compares with an annual consumption of approximately 20 million cubic meters. So, next slide. Okay. So, and as Latvia's Veneris, we are of course also actively involved in the forest management with around 10,000 hectares of own forest land and a tree nursery where we produce and sell around 1.5 million seedlings, especially grown to meet the future needs and quality requirements of our production. And the birch seedlings, which are on average 1 meter high, are strong and hardy because they have been grown in a nursery for 1 year in an open field. And such seedlings are mainly recommended for areas with potentially high proportion of greenery and make it possible to reduce the maintenance cost of the agro-technical maintenance cost. And in order to offer forest owners the opportunity to diversify their plantations with grow mixed stands, around 20% of the total production consists of spruce and alder. So, and now we come to a topic that starts for us in 2015, and it's now reaching its limits. You need to know that we produce our phenolic resin for gluing the veneers by ourselves, and we have also our own impregnation channels where we produce our surface films by ourselves. And therefore, our chemistry department, in cooperation with Stora Enso, has developed a method that reduces the content of fossil substances in binders. So we replace fossil phenolic resins with lignin. Wood consists of 3 main components, cellulose, wood sugar and lignin, and 1/3 of the wood consists of lignin, so this is the most common natural glue in the world. Lignin is a binder agent between the wood cells so that they are stuck together. However, lignin is used to be a useless byproduct of the paper industry and was mostly thermally processed. And this development of a new lignin-based binder has significantly reduced the CO2 footprint, formaldehyde and VOC emissions of plywood production and all the end products. And this is important without negatively affecting their technical properties. And as we produce our own phenolic resin-based glues and we want to implement these 100% in the increasing demand of our mills for lignin-based glues, Latvia's Veneris has decided to participate in the BioBond project. And the main goal of the BioBond project is to achieve zero use of fossil resources for production by 2050. This project was funded by the bio-based industry as a part of the European Union Horizon 2020 Research and Innovation Program. And Latvia's Veneris has taken the lead in this international consortium. The BioBond consortium brings together extensive interdisciplinary experience in the entire value chain, from the fractionation of lignin from wood-based refineries and to the production of different types of LPF resins. So that means lignin-based phenol formaldehyde resins. And this for various purposes. So the production capacity of the environmental friendly resin will reach 45,000 tons per year, and renewable lignin will replace more than 1/3 of the fossil materials used so far. The members of the consortium will use the new resin for the production and coating of plywood. This is what we are doing. And also sandpaper adhesives and binders for glass wool for thermal insulation. So, and the first step of the BioBond project is to reduce the fossil content in the resin by adding lignin. And Latvia's Veneris has developed a method that allows us to reduce the fossil content in resin binders by up to 70%, currently just under 50% by adding lignin. And we believe that in the future, it will be possible to use only renewable raw materials for production. So, and as already mentioned, plywood production also generates byproducts, and to be more precise, only 1/3 of the birch mass is used to produce plywood. The other 2/3 of the birch mass are byproducts. And in the past it was so that the only way to use these byproducts was to generate heat. And this naturally raised the question of whether there is the way to use these byproducts in other ways, and if so, with what added value for them. So, and we have found many applications for our byproducts. Most of the biomass produced is used in the local market, for instance, as chipboard, other press materials for packaging, pellets, and WPC supplements. We also export biomass, most of which is used in pulpwood production. A large part goes to biorefineries and is also exported as pellets and added to thermal utilization. And this part that is used for our own heating production is dry waste that cannot be used in any other production process, and birch bark. So, and in cooperation with the Latvian State Institute of Wood Chemistry, we have developed an innovative use of birch bark. It is betulin, or the birch bark extract. Betulin is found in the birch bark and is a main component responsible for the white color of birch trees. It is made by extraction from the outer birch bark, and it's known for its healing properties. So, and what does birch bark extract contain? The largest part is betulin with 60 to 97%, depending on the crystallization and purification parameters. The smaller part is lupeol with 2 to 10%, betulinic acid 2 to 6%, and tannins. And each of these ingredients have been studied extensively and offer many health benefits, such as betulin has shown some anti-cancer and antibacterial properties. Lupeol has also shown these properties and anti-inflammatory effects. And betulinic acid shows the greatest effects. And tannins are known for their antioxidant properties. And the greatest advantage of our birch bark extract is that it combines all the substances and therefore has a positive properties of all these substances. Yes, and thanks to this extensively studied properties of birch bark as an extract, many unique applications have been found. For example, in the food industry as a food supplement and additives in cosmetic as skincare, betulin can replace synthetic emulsifiers, preservatives, and antioxidant and psoriasis symptoms healing properties, and also in healthcare. Yes, and the birch bark extraction journey began in 2011 when Latvia's Fineres heard the word betulin for the first time. In 2016, in cooperation with the Latvian State Institute of Wood Chemistry, research into betulin extraction under laboratory conditions began. And in 2022, a pilot plant for betulin extraction called Betulin Lab was finally opened in Riga. And with this plant, we can produce up to 5,000 tons of raw materials for extraction annually, and the purity level can be increased by 99.8%, depending on the end application. So, and now we come to another innovative ingredient from the birch bark, and this is subboric acid. And the method for producing subboric acid was developed also by the State Institute of Wood Chemistry in Latvia. It has the potential to become a 100% ecological glue. Latvia's Fineres has acquired the license for the production of subboric acid, and the biggest advantage compared to conventional glue are its environmental friendliness, the elimination of fossil materials needed for its production, health benefits, and the efficiency which make it possible to glue wood to wood. The outer birch bark contains 30% of betulin containing extracts, 16.4% of the lignin carbonhydrate complex, mainly lignin, cellulose, and monosaccharides and polyphenolic compounds, and 53.6% suberin. Suberin acid and the lignin carbonate complex are used as a binders, which make up together 70% of the birch bark. For example, 3.4 million cubic meters of birch was felled in Latvia in 2017, and around 55% of this volume, so it means 1.9 million cubic meters, is industrial wood from which birch bark can be extracted. So in Latvia alone, around 20,000 tons of absolutely dry binders, agent, and other raw materials could be obtained that can be recycled. So, and in conclusion, we can say that the wood-based material birch has a lot of potential, and where we are ready to work as a specialist on sustainable solutions and implement these in production process and increase the added value sustainability of our products. Thank you very much for your attention.
Neste punto imos afondar nas innovacións no caso de Suecia e ímolo facer con Ewellyn Capanema. Ela ten experiencia en cargos relacionados coa innovación en diferentes biorefinerías dos Estados Unidos e de Canadá.
Good morning. I would like to start thanking for the organizing committee for the opportunity to be here on this really nice conference and in a really beautiful place. So I will continue on this line of now going from whole wood to wood components, and I was asked to talk about hardwood production, and I add a little bit of application. So we start with wood, right? This is some statistical data, and this is published by CEPI, the wood consumption in 2021. And what we see here is the ratio between hardwood and softwood. It's 30 to 70% hardwood compared to softwood, and the main species are birch and eucalyptus. So when we talk about the difference biomass, we don't have only the difference that we see in the field yesterday for the plantation, not plantation, for the oak forest. So not only the visual difference, but we do have a difference in the different components of the wood. And specifically for hardwoods, and looking for with eyes of a lignin, so we have less lignin in hardwoods than we have in softwoods. We also have less hemicellulose, but the most important is the structure is different. The ways that these lignins and these hemicelluloses are bonded to each other are different, and this will affect the way that they are processed to deconstruct the biomass, their properties and the yields. So then very fast we start with the feedstock. We have softwood, hardwoods, and in terms of the structure of lignin, so softwood is mainly G units, and it's started from the biosynthesis there with the coniferous alcohol. When we go to hardwoods, we have a mixture of coniferous, synapyl, and some species have large amounts of coniferous as well. So the idea is, as we go from softwood to hardwood and grasses, the structure of the lignin becomes much more complex. And the way to deconstruct the biomass, the oldest deconstruction pathway to deconstruct biomass is the pulp and paper industry. So, and inside the pulp and paper industry, we have different technologies, kraft, sulfite, organosulf, and now we have this boom of different biorefineries that are also using different technologies to deconstruct the biomass. And all these change the structure of the lignin that we will get to work with, and not even counting the difference inside each different technology. So this another data by CEPI. We do have 720 pulp and paper mills in Europe. And as we can see, we are using less paper, so the production of pulp and paper is decreasing. But why I'm talking so much about the pulp, it's because we are deconstructing the biomass. So when you deconstruct the biomass, you also get the lignin. But pulp and paper industry, the main goal is pulp, right, to produce paper. And this is showing here distribution of world total pulp consumption. And we see Europe is responsible for about 25% of the pulp, followed by, so the main one is North America, and then we have Asia and Latin America. Inside Europe, Sweden and Finland are the main producers, and we see here Spain with about 5% of the total pulp production. So, supposed to be two-stage here, but what is behind the little box there is that the value of the hardwood, the pulp in 2021 was about 170 million, and this is increased, and the prediction for 2023 is about 250 million in US dollars. But again, so we produce pulp and then we get the lignin. So, and just have a very simple math here. So in order to produce 1 ton of pulp, we need about 2 tons of wood. And when you do that on the black liquor that from the pulping process, we have about 340 kilograms of lignin. From this, we recover about 70% of this lignin when we talk something about the lignoboost process. So this brings us to about 225 kilograms of lignin that can be recovered. And then we look at the potential of lignin production. So just looking at the hardwood kraft pulp in 2022, this was about 80 million tons. So if now we look at the amount of lignin that we get per each ton of pulp produced, we have a potential of lignin production of 18 million tons per year. And why I'm talking about the potential? Because first, not every pulp and paper recover the lignin. Most of the lignin is used to burn for energy. So again, they are overlapped here. So lignin producers. The technical lignin, the majority of lignin available on the market is lignosulfonates. So about 80% of the lignin is lignosulfonate, about 15% kraft, and then we have another 5% that is for the biorefineries, hydrolysis, and soda pulping. In terms of kraft pulp or hardwood pulps, what do we see? We see lignoboost in Sweden that it recovers about 10,000 tons of lignin per year. And this can be used for hardwood and softwood, but both lignoboost and UPM with its facility in US used to be Dontar, is another 25,000 tons of lignin per year, mostly softwood, but they also can process hardwood. Then we have Stora Enso with the Sunila mill that was producing 50,000 tons per year, but we all know Sunila is closing its facility, so then there is a gap in the market now, because Sunila was selling lignin, but they will recover lignin in another facility. Then now we go to South America, we have Suzano that produced 20,000 tons of lignin per year and is eucalyptus lignin, it's hardwood. Then we have Klabin, 500 tons, that it switch between hardwood and softwood. And then I'm using just 2 examples of biorefineries, and both of them use hardwoods. And it's Fibernol, then it's in Estonia, and then Rematex that it's in the US. But we have to recover this lignin. What the process we have to recover this lignin? So the majority of the market is lignosulfonates, and so we start with the wood, and then there is a pulping process, and in the way that the lignin is recovered is through spray drying. And then if we look at the beginning close to the first box there, so there are different counter ions that are used during the pulping, and these will give lignins with different salts and with different properties. And lignosulfonates, they are water soluble. They are quite a different class of lignins. Then we come to the lignoboost process that was already talked in a previous talk. So after the pulping, the weak liquor goes through a series of digesters. And mostly after this concentration, this lignin was burned to generate energy. But then it can be recovered by using the concentrated black liquor, and is acidified by CO2, and then this lignin is precipitated, then it's re-slurried in acidic water, and then it decreases the pH, and then this lignin is precipitated. Oh, but why recover this lignin? Just because of the value of the lignin? Not really. So what we see here is that the pulp production can be increased 20% by removing some lignin. And what we see here on the x-axis is the extraction of lignin from different woods that have been pulped. And we see here softwood, birch, and eucalyptus, and we see that the different wood species will allow us to remove different amounts of lignin to get the same increase in the pulp production. But by removing this lignin, what happened is we decrease the concentration of solids and the black liquor, so then we have less energy, the combustion temperature is decreased. But then there is an amount of lignin that it can be removed that is still acceptable, the amount of energy that is lost. And what is showing here in blue is experimental data showing that when we pulp birch, so the combustion temperature can be decreased from about 1700 to 1400 by removing this lignin. So in the birch process, it's when we do the pulp and recover the lignin, so the industry can cope with removing more lignin compared to actually a softwood. So and what I'm showing here is the separation yield. So we have on the y-axis, this is lignin production, per solids, total solids on the black liquor, and then we have here softwoods, hardwood and softwood mix, then hardwood, and all this is kraft pulping, and then we have soda pulping. So then intuitively we would think, so as we decrease the amount of solids on the black liquor, it will decrease my yield of recovered lignin. And what we see experimentally that is not exactly the truth, because not only how much solids you have on the black liquor, but also how the severity of the process, how much degraded is this residual carbohydrate or the hemicellulose on the liquor that will cause us some difference in the yield. So in average, we can say that softwoods give a little bit higher yield of lignin based on the total solids in the black liquor compared to hardwood. But I can say that the hardwood is a little bit more challenged, exactly because of the interaction between lignin and hemicellulose and the structure of those hemicelluloses. Then another technology to recover lignin is quite similar to the lignoboost process. Again, the weak liquor goes through a series of digesters, and then it's concentrated. But then the lignoforce that was created in Canada, they introduced one step where they do oxidation of the black liquor. And they claim that this decreases the smell and make it easier to filtrate. Then the same process, acidification and then filtration, and in this case lignin, it's is washed on a filter press. So organosolv process, the most known is our cell process. So you have the biomass is pre-treated, so the pulping is done in a mixture of organic solvents. Our cell process is ethanol water. Then the lignin is solubilized, and it will be on this liquor that will be later precipitated in water or evaporated the solvent, and you get a very pure lignin. From another side, you have the pulp, that one of the issues with the cell process is that was directed, the cellulose part was directed to ethanol. That is quite cheap, kind of making this not economically interesting process. Then I want to talk about the fibrinol. This is a biorefinery. They have the first stage. It's steam extrusion process. So in the first stage, they remove the C5 sugars, and then it take the solids, do enzymatic treatment, and then separation. You have the C6 sugars, and then the crude lignin. They then went further, and they take the cake, they do an extraction with alkali, they solubilize this in alkali, they remove the hemicellulose, that is a plus on the biorefinery process. And then they take this lignin, it's an alkali, you have to precipitate and have a pure, they call lignova lignin. The other biorefinery is Rematics technology that use water. It's water on, it's a two-stage process, water on the subcritical stage, and then the solid removes C5, the solids go to supercritical water, and then they have the C6 and the omnopolymers, that is the lignin obtained with this process. Then if we put this all and compare, so what we see, we have different technologies, craft all the way to supercritical water hydrolysis. They all say they can use different feedstocks, hardwood, softwood. We know that some of them work better with hardwood than they work with softwoods. Different scales, the chemistry is different, and then the, let's call the extra beside the lignin, like sulfur, carbohydrate, and ash, are different content. If we go look deep into the structure of these lignins, we see that there is a variation on the amounts of the different functionalities. And in general, softwoods, they have higher molecular weight and higher TG compared to hardwoods. And then there are the dogmas. There is really a prejudice with hardwood lignin. So it's a lot of time, you can hear that hardwoods are not good for this and that application. So hardwoods are less reactive. Biorefinery lignins, they are waste, they are junk because they have contaminations, and by the contamination, here's this residual carbohydrate there. And then biorefinery lignins are considered low-value products. But when you look at the lignin and lignin application, everything depends what application you are using this lignin for. And then this concept that hardwood and biorefinery lignins are low value, it's really questionable. And I will give you just one example here. This is a use of different lignins in plywood PF resin. So it's 30% plywood PF resin substituted by lignin. And well, we see here the top line is the control, is the pure PF, and then we see here different biomass. We have hardwood lignin, softwood lignin, and grass lignin. And if we look at this, where all the curves coming together, so this we have a mix of, we have softwood, hardwood, and the grasses. And we can see that those are high purity lignins, and they are have the same performance. If we think about the chemistry, what is behind this biomass here is where we determine the amount of the reactive centers. Why hardwoods are considered less reactives? Because hardwoods, we have the two methoxy groups at the 3 position and 5 position, while the softwood have a 5 position free, and the grasses have the 3 and 5 free. But if we could see what is here, we can see that the best performing lignin on this application has the lowest amount of reactive center, and still it performs better when we compare the same parameters side by side. So what the conclusion for this here is that there is no correlation between the amount of the reactive centers, molecular weight, and performance in a specific application. So there is no disadvantage of using hardwood lignin compared to softwood and grass. And in terms of purity, so the same here, we see the high pure lignins, they have the same performance, while the best performed lignin here is a biorefinery lignin with about 40% carbohydrate, residual carbohydrate, and still is the best performance. So then I think is what we're talking about, this shift in metallity when we're talking about hardwoods and specifically hardwood lignins. So with this, I want to thank you all. Thanks a lot.